Hello, how are you? Hope you are doing good. So, we will resume the physics lecture regarding the graphs of displacement time, velocity time, and acceleration graphs. Acceleration time. So, what is displacement? Like I'm going to today, first of all, I'm going to define these terms. You might know what about distance. What distance is? Distance is a very simple thing, but about displacement, it is a little bit trickier. So displacement is a vector quantity, like we discussed earlier. That displacement is a vector. So displacement is a vector quantity that refers to how far out of place an object is. So this is the important how far out of place an object is. It is the object's overall change in position. So I am going to focus uh, on this line how far out of place an object is. It is the object's overall change in position. So previously we did an example of, like, for example, an object starts from this position, it moves up to this point, then it moves up to this point, then it sorry then it gets back to. So just consider that it started from position A, went to position B, then took a left turn, and then position D took again a left turn and reached position D, and then a final turn and got back to position A. The distance between A and B is, let's just say it is 10, and the distance between B and C is 5. C and D is again 10, and D and A is 5. So the question is that we have to calculate the distance that this object or this person covered and the displacement it covered. So the distance covered will be 10 plus 5 plus 10 plus 5. So that would be equal to 30. But and this is the distance. So now we want to calculate the displacement. So the definition of displacement is how far out of place an object is. So it started from this place, it ended up to this place. So effectively, it did not cover any distance effectively. So how far out means if it was somewhere here finally at the final position, if the person had stopped here, he had covered a distance or a displacement, a distance of 25 and a displacement of 5. So this point is 5 kilometer far out from this point, but when it started from A and got back to this position A, so effectively he did not cover the person did not cover any distance, it, displacement, sorry. So the distance is 30, but the displacement in this case is 0. Using the same example, just say that he started from A, then reached B, and then move to point C, and then move to point D in the same orientation. So he covered a distance of 10 plus 5 plus 20, 10, that is equal to 25. So he covered a distance of 25, but it is 5 kilometers far from point A. So the distance between point A and point D is 5 kilometers. So the effective distance he covered is 5 kilometers. So the displacement would be, the distance is 25, the displacement is 5. The displacement is 5. So this is the major difference between the distance and displacement. So uh, that is why it is known as a vector quantity, because in the vector quantity we have to like define a magnitude. So even though it covered a 25-kilometer distance in in these direction, but the effective distance was 5 kilometers in the upward direction. So this is the definition of displacement. The definition of velocity is the displacement divided by time, not the distance divided by time, but the displacement divided by time. Using the same example, using the same example, if the person started from A, then moved to point B, then to C, and then to D, and him, it took him, for example, it took him 50 minutes for the whole journey from A to D. So in this case, the speed, the formula for speed is distance over time. The formula for velocity is displacement over time. So in this case, the speed would be, the distance is 25 and the time it took is 50 minutes. So the speed will be 0.5 kilometers per minute, because the time we have taken is in minutes, so it would be 0.5 kilometers per minute. We can convert it into hours. Like if we can multiply it by 60, we can convert it into hours. But we have to compare it, so there is no need to change the units. So velocity is displacement over time. So in this case, velocity in this case would be, because the displacement is 5, the time taken was 50, so the velocity became 0.1 kilometers per minute. So now you can see the difference between the distance and the displacement, because he covered same, like initially the units are same, and it may seem that the speed and the velocity are same things, but as you can see, using the same example or the same case study, the velocity and the speed turned out to be different. So we will today we will talk about uh, both of these quantities: speed, velocity, displacement, distance. And finally, the acceleration is the change of velocity, not the change of speed, but the change of velocity per unit time. I'm going to write the definition for acceleration also. Acceleration is change in velocity per unit time. So let's solve some examples, and it might get more clear to you. I'm just going to erase all of this. So let's do an example for displacement time graph. Here is the statement: make distance time graph for a car starting from position A and reached a distance of 40 kilometers in 20 minutes, and then increased speed and covered the next 80 kilometers in 20 minutes with constant velocity. Here is a statement for the question, and let's see how we can make the displacement time graph or the distance time graph for this statement. So on x-axis, horizontal axis is the x-axis and this is the y-axis. Y-axis, this is the x-axis. So the statement says that make a distance time graph for a car starting a position from rest. So the car starts from this position and it reaches a distance of 40 kilometers in 20 minutes. So I'm going to mark these two values. This is the time scale that is equal to 20 minutes. This is the distance scale that is equal to 40 kilometers. So the important thing about the next phase is that it moves again with a constant velocity. So yesterday I told you about the increasing decreasing velocity, but that graph for a constant velocity is linear. So the difference would be it would cover a more distance in the next 20 minutes. So that it covered 80 kilometers in the next 20 minutes. So 80 plus 40 would be 120. So a total of 120 kilometers would be covered. And it covered the next 80 again in 20 minutes. So the total time would be 40 minutes. First thing what we can do is to convert the time in minutes into hours. 20 minutes divided by 60, that would be equal to 1/3 of an hour, 1/3 of an hour. So now we want to calculate the speeds. Speed in the first, like this is the rest position, 0 position, this is position A and this is position B. So speed from 0 to A would be the total distance covered, that is 40, divided by 1/3. So the speed in the first portion would be equal to 120 kilometers per hour. So now we want to calculate the speed in the next region, that is equal to A, the speed in the region of A to B. So that would be equal to speed is equal to total distance covered is again 40. The total distance covered is in the second portion is 80. So 80 divided by 1/3. So that would be equal to 240. This seems a little unreasonable because 240 is a very huge speed, but this was just to give you an idea of how we can calculate the speeds by using a distance time graph. If we want to create a velocity time graph of by using the same data, so the speed for the first from 0 to A is 120. So it would be like this for the first 20 minutes, then the speed increased to 240. So in the next 20 minutes, the speed increased to 40. So this is the displacement time graph for the same data. Sorry, velocity time graph. So this is the velocity time graph for the same data. So now we want to, if you want to find the acceleration of the same data, so the acceleration would be equal to 0 throughout the journey. It would be equal to 0. And why is that so? you can think of a reason. Like I'm going to give you 1 minute. So the acceleration would be zero because, uh, as I have told you, that in when the curve for displacement time graph is linear, the velocity is constant. So the acceleration is basically the change in velocity. So in this case, from either 0 to a or from a to b, velocity is not being changed. So in both these cases, from 0 to a or from a to b, the velocity is constant, and the definition of acceleration is the change in velocity per unit time. So the velocity is not being changed from 0 to a or from a to b. There is a jump here, but in this case the velocity is zero. In this case the velocity is also zero. Just ignore this part. So the acceleration for this whole example is zero. I'm going to make another graph for displacement time. So this would be the graph for velocity time for the same data, and this would be the graph for acceleration time using the same data. So this is distance time, not displacement time, distance time. This is velocity time graph, sorry, speed time, and this one would be acceleration time graph. Acceleration time graph. Acceleration time or distance time or speed time means that on the x-axis, of every graph, we would be talking about time. On x-axis, the variable would be time, and on the y-axis, in this case, the variable would be distance. In this case, it would be speed, and in this case, it would be acceleration. So, previously, in the last example, we did a linear line. So now we are not going to do the linear. We are going to make a curved line. I think I have, for example, a car started like this. When it reached this point, it got linear for some time. Okay. So initially it was a curve like this, then it got linear for some time. I'm just making it a little rough. Finally, the trend became like a decreasing trend. So now we want to calculate, or now using the same data, we want to make a speed time and acceleration time graph. Yesterday I told you that in this kind of shape, when the trend is increasing, we call this as increasing trend. Any shape that is curved like this, we call it an increasing trend. Like this, increasing trend, and like this, the decreasing trend. Straight lines are known as the linear lines. This is an increasing trend. This is a decreasing trend. So the distance time graph from 0 to A position is increasing trend, B is decreasing, and to up to C, it is a decreasing trend, increasing, linear, and decreasing. So that shows that initially it covered less distance as the time passed, but the amount of distance per unit time increased as the time passed. So the velocity time or speed time graph for this example would be like this. I'm going to complete the graph first, and then I will discuss that the reason behind this graph. acceleration time graph for the same would be, I'm just going to erase this line and draw this line at this position. So the acceleration time graph would be like this. You only have to get an idea of how distance time graph or how speed time graph works. So I'm going to explain it a little bit in detail so that this should be the last example for this lecture. Initially, if we compare this graph with this one, I have already done that, so there is no need to compare it again. But as we can see, in the if we divide this time into four parts, if this is the time for from 0 to a, I draw a line with another color. So this is the time from 0 to a, and I'm just going to divide it in four equal parts: 1, 2, 3, and 4. Now I'm going to compare how much distance it covered in each part. So the distance covered in this part is this. The distance covered in this part is this. The distance covered in this part is this. And the distance covered in the last part is this. So now as you can see, the distance covered in the first part is smallest. The distance covered in the second part is a little greater than the distance covered in the first part. Then it gets more bigger, and finally in the last part, the distance covered is the maximum. So what we can deduce from this graph is that as the time passes, the car is getting more faster. So because when we divide it into four parts, initially in the first part the distance it covered was smaller, but as the time passed, the distance covered by the car increases per unit time. So say these four parts as per unit times. So the distance covered per unit time increased. So that means the car is getting faster. So if the car is getting faster, then the speed of the car should increase. So the speed of the car, it started from zero, like as shown in this graph, it started from zero, and then it increased and started increasing up to the point A. So this is the graph for an increasing speed. So the speed kept increasing until it reached point A. From A to B, if we divide this portion in four parts also, like I'm just going to draw some lines so that I can compare it. So this is the time for distance covered in A to B, and I'm going to like divide it into three or four parts just for your understanding. So I have divided it into three equal parts. Let's just see what happens with the distance covered. So as you can see here, the time as time is divided into three equal parts, the distance covered by the car in this region is also same for all of these intervals. So as you can see, this gap is same. So that means as the time passed, the car covered the same amount of distance in per unit time. So the car speed was neither increasing nor decreasing because it was covering a constant distance on in each interval of time. So this means that just consider that this is some speed, any number. So this speed would remain constant until, or it remained same until it reached the point B. So let's do that trick again with B to C. I'm going to again divide this into four parts. 1, 2, 3, and 4. Now just to check how much distance it covered in each part. So this is part 1, this is part 2, this is part 3, and this is part 4. So as you can see this, in the first part the distance covered is the greatest, exactly opposite to this, because in this and in the trend from 0 to A, the distance covered in the first part was least, but in this case the distance covered in the initial part was the greatest, and in the final part it was the least or the minimum. So the amount of distance the car covered in each unit of time or each interval of time was decreasing. So we can say that the car was either slowing down or it was losing speed. So that is why it was covering less distance in each interval of time. So we can show that in this graph that as the time passed from B to C position, the speed of the car was decreasing. So in this lecture, in this and the previous lecture, we have talked about how we can find the velocity or the speed from distance time graph. In some later lecture, we are going to find if the speed time graph is given, how we can calculate the distance from a speed time graph, how we can do the opposite of this. Now we can find the speed from the distance time graph, the values, but how we can calculate the displacement using this graph, we have to do exactly the opposite, but we will learn it in some later lecture. So now we have a speed time graph. So using the same analogy as we have used in the distance in converting the distance time into speed time graph, we can say that in the first region from 0 to A position, the acceleration was constant, because again, if I divide it into 3 parts, this, this, and this, then you can see that the velocity in each part is almost constant. So the change in velocity per unit time in each interval time was constant. Acceleration in the 0 to A phase is constant value. It is not changing from A to B. So the acceleration in this part would be 0, and as the speed is decreasing from B to C, so the acceleration would be negative in this part. So that's it for physics.